All right, hello everyone. We are from the HL and Texas Robotics Lab from ETH Zürich, and we'd like to present you today a very interdisciplinary project, including architects, civil engineers, material scientists, and of course, roboticists. So let's get started. Inside of the white protective layer in this video you're about to see is a construction site where new digital building technologies developed at ETH Zürich are evaluated and applied to real-world application. Once completed, this digitally fabricated house or building unit will be inhabited by humans for years to come. Our robot, the in situ Fabricator, does one part of this project by semi-autonomously building a steel wire mesh, which acts both as reinforcement and formwork for an undulated, full-scale load-bearing concrete wall. "22,000 welding nodes and 125 production hours later, the robot fabricated a 12-meter long, 3-meter high, and averaging of 8 centimeter thick, S-shaped steel wire mesh. And the only part missing is to manually fill the concrete, the mesh with concrete to end up with the desired wall, which you see here. So our work and the next 10 minutes are focused on the sensing system required for the accurate and adaptive fabrication of the steel wire mesh directly at its final location. Such a wall must be built in situ, which means on site, so that it's rigidly coupled to the existing structure. So let's start with the motivation. This novel digital fabrication process you just saw in the video is called mesh mold. Mesh mold consists of robotically fabricating a steel wire mesh which acts both as reinforcement and formwork for reinforced concrete structures. It generates lower waste because otherwise a negative of the wall would have to be built out of wood to form the shape of the wall. This robotic process is also cost efficient since it is estimated that building a curved wall like the one we built would cost almost twice as much as if it was completely built by hand. We chose to focus the system autonomy on ensuring the building accuracy without operator intervention. So the system is supposed to manage its own accuracy, which would be the hardest for the operator to do. As mentioned, the wall will be part of a digitally fabricated building unit, which will finish end of this year. And here you can see a rendering of that building unit. And if you look closely, you might find our wall. It is located at the ground floor, label A in the rendering, and we'll have 2 stories on top of it with people living in them. So let's start from the beginning. What were the challenges? First of all, the wall must be built with a global accuracy of ±2 centimeters because a 3D printed floor slab will directly be fastened on the top of it. Any larger errors create conflicts as the additional building components are added to complete the building unit. Secondly, the system needs to be able to build accuracy in the presence of dirt, temperature changes, and non-smooth and non-flat grounds. So we are outside, so the environment constantly changes over the whole building process. The system must also be able to handle the unpredictable nature of this specific building process. And for this, you see the video. While building one layer from bottom to top, the mesh is attached to the robot. Only when we are at the top of the layer, as in the video, the mesh is released and is returned to its relaxed natural position. So what we observe is that internal tensions build up within the mesh during construction, causing it to deflect away from its built position once the robot releases it. So this behavior is very hard to prevent and hard to predict, so we need a system that monitors the accuracy of the built structure and adapts the building plan on the fly to compensate for errors which build up during construction. This is called adaptive fabrication. In addition, since the wall is 12 meters long, our mobile robot needs the ability to reposition its base and continue building. Finally, to give the system true mobile autonomy, we wanted to develop a sensing system that is fully on board the robot. While sophisticated commercial solutions, for example, a Leica tracker, could have been used, we wanted to show that we can get sufficient localization accuracy using simple off-the-shelf cameras. Because of these challenges, and to the extent of our knowledge, no mobile robot has previously built such a full-scale load-bearing wall directly on the construction site. So how does our sensing system work? Well, we use two complementary onboard camera-based sensing systems that are used to enable the construction of the steel wire mesh. This picture shows the tool head mounted on a robot's end effector from below. The first system, this camera here looking down to the wall's base plate, detects fiducial markers to localize our robot in a globally consistent reference frame and with high accuracy over many repositioning maneuvers. The second system, this stereo camera setup here, pointing to the built mesh, detects the contour of the constructed mesh to feed back the as-built position of welding nodes. Finally, we combine these two systems so we can express the sensed mesh contours in the global reference frame to ensure the accuracy of the built structure or the built mesh. All right, so let's discuss the global robot localization. As mentioned, we detect fiducial markers, in our case, April tags, or just tags, which are visible at the bottom image. And we measure their relative pose with respect to the camera. Prior to building, we generate a map of the fiducial locations, which is aligned with the CAD model of the wall through a one-time calibration procedure. Since our world frame is defined in the CAD model, this calibrates the global pose of all our fiducials or of all our tags. After the robot is repositioned and its support legs are lowered, the arm is moved to different locations to take multiple measurements of the relative fiducial poses, and the new robot pose, the new global robot pose, is optimized. The arm can then be reattached using inverse kinematics, and building can continue. We also show a way to improve the accuracy of the system, and we validate it with ground truth measurements. We found that the tag measurements should be taken from a similar distance, angle, and region in the image frame as they were taken during calibration. In that way, the system global accuracy falls below 0.5 centimeters and 0.15 degrees, which is 3 times less as opposed to taking tag measurements from random camera positions. By mounting the localization camera on the end effector, we have the flexibility to carefully choose the poses from which the fiducial measurements are taken. And therefore, we can ensure a global robot pose estimation with improved accuracy. Okay, so let's have a look at the second system, the mesh detection. At the top, we see a video of what our mesh detection cameras see. The goal of this subsystem is, as I mentioned, to detect the contours of the last layer of the mesh that was built so that it can be compared to the original CAD design. To do so, our wide baseline stereo camera pair mounted on the end effector is able to locate elements, in particular welding nodes, at the leading edge of the mesh. For this, there are two main steps. First, in the middle image, we use edge detection to find possible candidates for our target welding node. Secondly, we try to find the correspondence line pair that projected to 3D is closest to our CAD model. So in other words, we minimize the measure of the quality of the match to the CAD model. You see the output of the algorithm in the bottom image, where the two correspondence line pairs, orange and blue, represent the target welding node. This is done for all other welding nodes of the recently built layer to get the complete 3D information of the mesh contours with respect to the robot. With the robot's global pose estimation, we can express it in the world frame. So the combination of the two presented complementary sensing systems enable us to measure the mentioned deflection of the mesh globally and to actively adapt the building plan on the fly. The building plan adaptation is done by changing the angle of insertion between the wire that connects two layers through welding. This essentially adjusts the path of the mesh in the horizontal direction to bring it back to desired shape. So it is this iterative sequence of building, scanning, correcting, building, scanning, correcting, and with this, an accurate and collision-free fabrication of the mesh is possible. So this image shows the accuracy of the fabricated mesh versus the original CAD model, as measured doing ground truth measurements with a high accuracy laser scanner. Red are errors over 2 centimeters, orange and yellow is between 2 and 1 centimeter, and green are errors below 1 centimeter. From the plot, it can be seen that the errors are highest towards the top of the mesh in a region of high curvature. This is where the deflection of the mesh is the highest. While we observed during tests in the lab that these deflections would have been significantly worse without the building plan adaptation, this indicates that there is still room for improvement, and we plan to investigate the adaptive fabrication strategy further in the future. So in summary, 98% of the total geometry is within 2 centimeters of the designed position. The average error is around 9.5 millimeters. So that brings me to the conclusion. We have presented a system to enable the on-site fabrication of an undulated steel wire mesh on a real construction site, which, through a novel digital building process, has become a load-bearing reinforced concrete wall. Our sanding system enables the robot fabrication of a novel, labor-efficient, accurate, and waste-free digital fabrication process. To the best of our knowledge, this is the largest structure that has been built by a mobile robot using solely camera-based sensing. Its accurate construction was only made possible through a novel adaptive fabrication strategy. We think this represents a significant step forward for on-site robotics building construction. So thanks a lot for your attention.